So, hello everybody, another great session of ROMER Talks. Today our visitor is Burak Boyacıoğlu, earned his PhD from University of Washington, William Boeing Department of Aerodynamics and Astronautics in 2022, very recently. He holds a Bachelor of Science degree in Aeronautical Engineering, a minor in Mechatronics, and a Master's in System Dynamics and Control, all from Istanbul Technical University. All completed in 2013, 14, and 16 respectively. His research interests include optimal sensor placement, active sensing strategies for highly sensed systems, with applications in biological flight and engineering flight and space systems. He has been recently a postdoctoral scholar at the University of Nevada, Reno, and he is now teaching a graduate level course. And he has taught a graduate level course for professional students in University of Washington. He is also currently a visiting scholar and teaching digital cultural systems in also ITÜ. Okay, now let's hear his amazing presentation and see what he's talking about.
Thank you for the introduction. I'm teaching this digital control design course based on Mert Hoca's lecture notes. Otherwise, teaching a course from scratch it's a burden. So I'm glad that I have some notes from Mert Hoca. Oh, so yeah, today I'm going to talk about active sensing and sensor placement. My postdoctoral studies were on biological flight. We studied an flying insect called hawk moth. Okay, yeah, good. Okay, yes. In Turkish we call it güve, but this is a special güve. The wingspan of this güve is like 10 centimeters, so it's quite big, but it is able to make some agile maneuvers thanks to its gyroscopic sensing skills. So during my PhD, I tried to understand its strain-sensitive sensors, the information delivered to the central complex of this animal through neural encoding. So I did research on the effect of neural encoding in observability of the gyroscopic variables like pitch rate, roll rate, and yaw rate. So they have these sensors all over their wings. Company form means the shape is like a bell, as you can see here. When there is some pressure on it, it triggers some chemical reaction. And there are like hundreds of sensors throughout their wings, especially on the veins of the wing. So this was my doctoral studies. And during my postdoc, I studied another flying insect called fruit fly, sirkesineği or meyvesineği. So these flying insects, they are able to find this source of the food just following the wind. Of course, there is some visual stimulation, but we assume that there is no visual stimulation, but they are pretty good at finding the source of the food. And they smell the food, and the smell comes with the wind, so they have to determine the direction of the wind, but they don't have a direct sensor to determine the wind direction. So they have to make some calculations, and I try to understand their behavior. They follow some interesting trajectories. So I try to understand their trajectories, where they use these trajectories to estimate the ambient wind direction. So I would like to talk about observability at this point. You don't have to measure everything you are interested in a control system. You can extract that information indirectly. So in this case, for me, observability is everywhere. For example, when you are talking to a friend of yours, they won't tell you about their emotions, but you will read their faces. That's your measurement, and you will interpret those signs, and you will decide if they are upset, if they are sad, if they are happy. So that's what we call observability in control. So you don't have to measure everything, but you can extract that information. And if you can extract that information, then your system is observable. Another example is from soccer, football. Let's see. So there was a corner kick here, and something happened there. We couldn't see it. Let's see it again. Okay. So the question in football is if the ball crossed the line or not. And from this perspective, you can't really tell. So you have to change your perspective to be able to tell if it is a goal or not. So that's what I call active sensing. So you have a referee, and they have to be in the right position to be able to tell what you are interested in here. So that's again the state of the ball is the thing you want to estimate, and you have to actively sense its position to decide if it is offside, if it is goal, etc. So more formal definitions. So we have a block diagram here. Probably you are all familiar with these block diagrams. You have a system, a dynamic system. You have the model of the system. You don't have the exact system, so there is some uncertainty in your model. And X describes the system state. You have state variables there. And you have some noisy measurements from your system. And you filter those measurements and get your estimated state. So you don't have to measure all the state variables, but eventually the goal is to estimate all the state variables. And then you compare your desired state with the estimated state, and that will give you an error, and you take actions according to your error information. And I'm interested in this sensing part. So let's say we have this nonlinear function g, which is a function of the state of the system, also the control inputs, and you have the measurements. So you know your measurements, and we assume that you know your control input because you are sending that signal to the system. So the question of observability is, can you determine X from your measurements, also from your input information? And if the answer is yes, then your system is observable. Otherwise, your system is unobservable. This is the binary definition of observability. And there are some analytical and numerical tools to determine the observability of a system, either nonlinear system or linear system. So if we go back to the hawk moth problem, they have these sensors on their wings. And these sensors, they send the neural encoded information to the central complex of the flying insect. There are two questions I ask at this point. First, the measurements are delayed. So how do you determine the observability of a system if there is some measurement delay? And the second question I asked is, since that neural encoding, it acts like a composite output function. So how do you determine observability of a system with composite output function? That's the second question I asked. Today, I'm going to address this question, not the first one. The first one, because we have limited time. But I also addressed that question. I think that paper also includes this answer, so you don't have to go to SciTech paper for that. If we go back to the fruit fly, we are trying to understand these trajectories they are following. So we assume that they want to estimate the wind direction. So they want to estimate the wind direction, they want wind direction to be observable. And if you can quantify observability, that's great, because we assume that these trajectories are maximizing observability of the state variable we are interested. So there are two questions I asked here. First of all, the fruit fly, it knows what it is doing, but their dynamic model is not perfect. So there is some uncertainty there. So the first question I ask is how to quantify observability of a system if there is some noise. It can be either process noise, or measurement noise. The second question we ask is the quantification of observability of an individual state variable, because we know that, but we assume that they are trying to maximize the observability of the wind direction, not all the other parameters. So what if we just focus on one individual state variable? Then how do you quantify the observability of that variable? That's the second question I ask, and I will try to answer it today. And by the way, fruit flies, they are quite amazing animals. They are sharing like 6% of our DNA. And so there are lots of studies based on fruit flies, and like it is complex enough, but also simple enough, I guess. So this is the brain of a fruit fly. It is mapped. It was mapped before, but this is like an improved version of it. So there are like 50 million connections there. Again, it's simpler than a hamster. So lots of scientists, they use this as a benchmark problem or benchmark system. And this was our setup at University of Nevada, Reno. So we want to make sure that these flies are detecting the smell, but you can't really make sure of that. So we have this system, and we have the genetically modified fruit flies. So when they see red light, they think that there is a stimulus. There is a smell, but there is no actually real smell. But they just smell that, and they try to locate the source of that smell. And what they do is they follow the wind. So we have this small wind tunnel. There are no visual stimulus for the fruit fly. Instead, when they get the red light, they think that there is some stimulus. And we have like 12 cameras in this setup, and we are able to follow their trajectories, observe their trajectories. That wasn't my research. I was more interested in the in understanding an average trajectory of a fly. So a little bit background on observability. So let's say you have this mass spring damper system. You write the equations of motion. It's a second order differential equation. Then you write it in a special form called state space form, right? In this form, you have like two first order equations. And these are your state variables, x, the position, and the velocity is v. And you have the input f. So this is A is the system matrix, and B is the control matrix. And let's say you are able to measure the position. So Y will be in this form. So C is the measurement matrix. In this case, it is just a row vector. So if you are able to measure the position of the system, you can just take the derivative and obtain the velocity information. So both state variables are observable. So the system is observable in this case. But if you are able to measure just the the velocity of the system, since you don't know the initial position of the system, you can't determine x. And in that case, the system is unobservable. Since this is a simple system, it is easy to determine the observability of a system, but it is not usually the case because systems are more complex. So you need more complex tools to determine the observability of a system. So let's say you have a discrete time, linear time invariant system. What you do in this case, you just write down some measurements. Measurements, you know them. You have a model of the system A, B, and C. You assume that you know those parameters as well, and you assume that you know the control inputs. The only thing you don't know here is x0. Then what you do is you put everything on the left-hand side, everything you know. And on the right-hand side, you have x0, the initial state of the system you want to know, and you have the observability matrix, CA square up to CA to the power n minus 1. And if that matrix has a left inverse, if it is full rank, then your system is observable. You can determine x0 uniquely, otherwise your system is unobservable. And just notice that observability matrix, we use it to determine the observability of the system, but it doesn't include U in it, or it doesn't include the B matrix in it. So we can say that linear observability is not a function of the trajectory you are following. It's not the case for nonlinear systems. Another note is that if you take, so these are my measurements, and this is the collection of measurements, this vector. If you take the derivative of that vector with respect to x0, it will give you the observability matrix. So you can see the observability matrix as a sensitivity matrix to the initial state of the system. Another tool we use is the observability gram mean. Now, in this system, as you can see, I don't have B or U because I know that they don't affect the observability of a linear system. So I have autonomous dynamics. To obtain the observability gram mean, I write the output energy of a collection of outputs. I obtain this expression here. So this part is a function of the initial state, but this part is independent from the initial state of the system. It is constant. It depends on the system matrices. So I call that matrix as the observability gram mean. And actually, this gram mean matrix is related to the observability matrix. The gram mean matrix is the product of the observability matrix transpose and the observability matrix itself. And interestingly, you can obtain x0 from this equation where you need the inverse of the observability gram mean. So you can use the full rank condition to determine the observability of a system. So your observability gram mean should be full rank, invertible, if you want to uniquely determine x0. And hopefully it shouldn't be just full rank, it should be well conditioned. Preferably if its eigenvalues should be like equal. It is the ideal case. So we use the condition number, the ratio of the maximum eigenvalue to the minimum eigenvalue of this matrix as an observability metric. Let me show it to you. So to quantify the level of observability of a system, we use the observability matrix, observability gram mean eigenvalues. So in the ideal case, the eigenvalues should have closed values. In this case, the ratio is far from 1, and it's not good because it introduces inverting the observability matrix. A gram mean introduces some numerical errors if the gram mean matrix is not well conditioned. So that's one of the observability measures we use. The condition number should be close to 1, the number 1. So if you are placing sensors and you calculate some observability gram means, you will aim to minimize the condition number of the observability gram mean. There are other metrics we use or measures. So you can use the minimum eigenvalue of the observability gram mean as a metric. It is the least observable direction in your observation space, and you want that least observable direction to be as observable as possible. So another metric you can use is the minimum eigenvalue. So you may aim to maximize your minimum eigenvalue by placing your sensors at the right locations. Or you can use the determinant of the gram mean, which defines the volume of the observable space. So this is still background literature review or review of tools, existing tools. If you have a nonlinear system, so in this case, our nonlinear system is in a special form. So
what was your state? So you said that like eigenvalue of premium is like minimum for your premium matrix and so on, but we don't know your states.
yeah, it can. Yeah, I'm just introducing general. Yeah. But it can be your position and velocity, but your eigen directions won't be in those directions usually. But yeah, it can be anything. So here we have a nonlinear system in a special form. We call it control affine form. You have the drift term here. Without the input, the system will drift according to this function. It can be a nonlinear function, and you also have these functions here. These are also a nonlinear function of x, and you can also have a nonlinear measurement function. In this case, what we do is we take the derivative of the measurements. So we have hx there, then we have y dot. Sorry for these complicated formulas, but I'm just giving the steps. At the end, we have this notation, Lie derivatives here. So a Lie derivative of h with respect to f0 would be like take the derivative of h with respect to the vector x, then multiply it with f0. That's how we define Lie derivative. So instead of this complicated formula, I just use this notation. Eventually, we obtain some nonlinear functions. We don't have just hx, but also we have the Lie derivatives of hx with respect to all the vector valued functions f0 up to fm. So we have these functions, and these functions, again, we want those functions to span the whole state space. So they should be interesting enough. That's how I call it. Like if your rows are the same, it doesn't introduce any new information in a matrix. Of course, it does introduce some information, but you can make it interesting if your rows are linearly independent. So in this case, you want these functions to be linearly independent. And so this is the observation space G, and you take the Jacobian of that expression. And if it is full rank, again, the condition is being full rank, then your nonlinear system is observable. We say weakly observable because it depends on the trajectory you are following. Now, these functions, they matter. And so now your input, the trajectories you are following, matters for observability. And one final tool I want to introduce is the empirical observability graph mean. So let's say that you have the finite element model of your dynamic system, and you are able to stimulate it. Let's say you have this nominal input u0, and you have the initial state x0, and you get some measurement y0. What you do is you perturb each of your state variables one by one, and you obtain different outputs. Since we said that observability matrix is the sensitivity matrix, that's what we are doing. We are calculating the derivative, but in a numerical way. So we have n state variables. So we need like 2n simulations. Eventually, we get the observability matrix in a numerical way. And again, we want this observability matrix interesting enough, so it should be full rank. Since this is a numerical method, you can't just guarantee observability, but Nathan Powell from my lab, he showed that if this graph mean matrix you obtain from the observability graph mean you calculate here is full rank as the perturbation amount goes to 0, then your system is weakly observable, you say. But calculating this limit is also not like easy, usually not possible, because that's why we are using like this tool, right? Because analytical tools are limited, then we need a numerical tool to determine observability. So once you obtain the observability graph mean empirically, in this case, you can use its eigenvalues again to quantify the observability of a system. So that has been the review of the material on observability. And let's go back to the flying in sec hawk mode. So this is the hawk mode. I just wanted you to see the behavior of the animal. There's a flower here and is interested with the flower here. So one slide further. Okay, so we modeled the wing of this system. Simple model. We have a rectangular plate here. What we do is we write the equations of motion. We have a second order differential equation here. K is the stiffness matrix and M is the mass matrix. And PQR, we don't know these variables, pitch, roll, and yaw rates. We want to determine them from the strain information. And here you have the model coordinates. So you can obtain the strain information from those model coordinates. And your inputs in this system are Q dot, P dot, and R dot, which are the rotational rates, not rotational accelerations of the system. And we are neglecting the aerodynamic terms here. I gave this presentation 3 days ago to the aerospace engineering, and they didn't like this assumption. Well, aerodynamic, are you neglecting those terms? I'm neglecting that because I want a simple system, because I'm especially trying to develop some analytical tools. And if you have lots of complex terms, analytical terms, they become limited. So what we do to analyze the observability of the system, we write the system in this special form. So it is in the state space form. These are the state variables, model coordinates, and their derivatives. And we have PQR, they are unknown. And we know P dot, Q dot, R dot, those are the inputs we are applying to the system. If we calculate the, and we are assuming that we are able to measure the strain as a combination of model coordinates. If you write down the observability matrix, just using the drift term F0, so this is F0, your system, your observability matrix is not full rank. So your system is unobservable if your system it does not have a control input. If you consider at least one of the control vectors, so these are the control vectors. If you consider at least one of them, then your system becomes observable. So that is, you have to move to determine PQR. You have to have an action on your system to be able to determine P, Q, and R. So this was a study done again in my lab in 2015. But in my case, I'm going to assume that this strain information is not immediately available. It is neural encoded. By the way, I'm not talking about neural networks. I'm just focused on one single neuron. So the question is, what if the output is neural encoded? How does it affect the observability? So let me introduce the neural encoding model we are using. So the stimulation triggers some spikes, and neurons are delivering the spikes to the central complex of the animal. So in this experiment, what they do is they stimulate the system, and each time a spike happens, they just look back and they try to see what triggered the spike. And then they take the average of those trigger events, and that is called the spike triggered average. And if your new signal is similar to this signal, this stimulus, then there's a high possibility of a new spike occurring. So this is from a biology paper. Let's see a more mathy version of it. So we have the stimulus, the strain information comes, and if it looks like the spike triggered averaged, it will give a big number to us, and we scale that number, and the probability of firing of a spike is calculated using this nonlinear activation function. So if the value is close to 1, the value obtained here close to 1, then you have a high probability of firing as your output of the system. I'm going to use the probability of firing as the output of the system. Actually, the output of the system is the spike itself, but it makes the system discrete, and I didn't want to have that complexity in my system. And NLA function, it's like a saturation function. It has these parameters, and the biology people I was working with, they were trying to understand the effect of these parameters C and D on the observability of the system. So C determines the slope, and D determines the location of this this shape in the system. But they were just doing some experiments, and I thought, like, if we have a analytical function, we should work on it instead of just trying random numbers. I will call this variable as projected stimulus, by the way, in the future. So we need to develop some tools to understand this behavior. By the way, this system, it has output delay because this operation requires to look back in the previous strain information as well. So the output of the system is delayed. That's why I studied that problem as well. But today I'm just interested in this NLA function. So we had this variable here, projected stimulus. NLA function is like a composite function on this system, and I'm trying to understand its effect on observability of the system. That's what I summarized. So I just simplified the system. Let's say that there is no input. You have just a nonlinear function of the system state. The question I ask is, if you can comment on the observability of the system with this output function h of x, can you comment on the same system with the output function g of h of x? In our case, g is the NLA, the nonlinear activation function. Again, we were able to comment on the observability of the original system, right? We checked the rank conditions. It was observable, but can I make it more observable or less observable by putting this neural encoding on it? That's the question I asked. So we built the observation spaces. You have the Lie derivatives of h here, and you have the Lie derivatives of g of h in the second case. So can you relate these observation spaces? That's the question I asked. And the answer is yes. If you take the Jacobian of those expressions, they should be full rank. And for observability, and I found this expression, I just observed it first, then I proved it. So I was able to find their determinants are related, and a determinant, if it is equal to 0, then your matrix is not invertible, right? So this result tells us if the first system is the original system is unobservable, you can't make the second version. You can't make it observable by just adding a function on it. That's the first outcome I obtained from this result. So if the original system is observable, you can't make it observable by adding a function on your output function. Maybe it is obvious, but it was not proven. And the second, you can even make your system unobservable if your derivative is equal to 0. Then even if it is your original, if your original system is observable, you can make it unobservable. That's the second conclusion I had. So let's see a very simple system to understand this. Let's say you have the system, a double integrator, and you are able to measure the first state variable. This is the observability matrix you obtain, and it is full rank. It is obvious. The determinant is 1 here, right? So the system is observable. You can obtain both x1 and x2, both state variables, based on one measurement. But let's say you have a saturation function on your original output function. You can use some analytical tools, existing analytical tools, to determine the observability of the system, or you can use my result to do the analysis here. So what you have to do is you already check the rank of this matrix. So you just need to check the derivative of this function with respect to x. It shouldn't be equal to 0, otherwise you are making the system unobservable. So that's the derivative of the function. So that's how you can make it observable. Let's see a figure on it. So the bold one is the straight line is the function itself. The dashed line is the its derivative. Its derivative is equal to 0 here, and it is equal to 0 here. And yes, if your x1 is in this region, your system is unobservable, because you can't, let's say x1 is 5, you get 1 as a result, as an output. If your x1 is equal to 10, you get 1 again. So you can't distinguish two cases. And you can see it from its derivative as well. Like, the derivative shouldn't be 0. If it is 0, you can't determine your system's state. And let's go back to the neural encoding. So we had this model, we had this NLA function here. We take the NLA function's derivative with respect to the projected stimulus. So here I have two different NLA functions. So if your projected stimulus is in this interval, you should use the red neural encoder to be able to observe the rotational rates you want to observe. But if your projected stimulus is in this range, then you should use the black neural encoder for maximizing the observability of the system. So instead of having these, I wouldn't say random, but now we have a mathematical approach to an analytical approach to understand these parameters C and D. And let's say you are obtaining your projected stimulus from a numerical method. That's okay. We can still comment on observability of the system. I think that's one of the perks of this approach, or this result. Do you have any questions so far before I discuss the stochastic observability? This this one is red.
Okay. I'm colorblind.
Yeah. Really? You can't say?
Yeah.
Okay. I usually try to make sure that.
All of them are black.
Okay.
Yeah.
Okay. Sorry about that. Okay. So the derivative should be non-zero. In this region, it is 0. That's why in this region, I shouldn't use this nonlinear activation function. And in this region, the black one is 0. Yeah. Yeah, you can, if you can. Like, the probably the HawkMod is not doing that, but they have like hundreds of sensors. So maybe some of them are programmed in one way, and the other ones are programmed in the other way. That's why they are able to determine the rotational rates, and they need that many sensors. That was the question we wondered, actually. We asked, like, why they have like hundreds of sensors, like 5 of them or 12 of them were enough. But this result also like helps us to understand that. I'm going back to the fruit fly. So it's a totally different problem, but I'm trying to develop some observability tools to understand that problem. So let's go back to the fruit fly. Again, it has a dynamic model of its flight, but it is not perfect. So that imperfection, I model it as uncertainty. So like we can think it as process noise. Or there are also some uncertainties in your measurements. For biological systems, it is not easy to determine the level of unobservability. For engineering systems, maybe you can use data sheets of sensors. So how do you quantify observability of a system if there is some noise in your system? So far I didn't discuss noise. In the previous section, there were no noise components. And the second question I asked is, how do you quantify observability of an individual state variable? Let's say it's the wind direction in the presence of noise. Those are the two questions I asked. So we are getting help from like information theory. Let's say you have X, you want to estimate X, and you have the estimation of X. We call it X hat. So the error covariance of your estimator is bounded by the Fisher information matrices inverse. So even if you have a perfect filter, there will be some error because of the uncertainty in your system. Think about the Kalman filter. For linear systems, it is the ideal filter because it satisfies this equation. For Kalman filter, the Fisher information matrix is equal to the error covariance matrix. So there is always some uncertainty. Your estimation won't be totally smooth because of the noise effect. So we built the observability matrix considering this uncertainty. Let's see a dynamic system here. In this case, we have again an autonomous system. There is no control input here. We have some Gaussian noise both on our model, also on our measurement model. So what I do is I just build the vector of output functions throughout time. W is my window size, and here you go. We have the observed matrix here. It appeared here. X0 is the variable I want to estimate. It's the whole state vector, and there are these noise terms here. What I do is I calculate the Fisher information matrix of the collection of outputs with respect to X0 because I want to estimate X0. And it has a nice form, right? We have the observability matrix here. We have this huge matrix in the middle. And we have the observability matrix again on the right-hand side. So I'll call it stochastic observability grammene. The problem with this formulation is this matrix becomes bigger and bigger and bigger if your window size is huge. Like let's say you have 3 sensors, you have 3 outputs, and let's say you are considering a window size of 100 time steps, then you have a 300 by 300 matrix, and you don't want to invert that matrix actually. So this formula is not great. But I solved that formula, and I will give you a sneak peek at the end how we avoided that matrix inversion. But let's not focus on that. We need to calculate the stochastic observability grammene, and once you calculate it, you can use its eigenvalues to determine the observability of the system, as we did it for deterministic systems. So I think I have. Oh, and if you want to estimate one state variable, here is what you do. You build the observability matrix, you obtain the Fisher information matrix, and next you invert the Fisher information matrix, and all the diagonal elements are corresponding to state variables. If those variables are small, like these diagonal elements are small, then the corresponding state variable is more observable. And if you can't invert the Fisher information matrix, that's because one of your state variables, at least one of your state variables, are not observable. In that case, what you can do is you add the identity matrix, let's say, to the Fisher information matrix multiplied by lambda, and you take the inverse of this expression as lambda goes to 0, then you will have infinity if your state variable is unobservable. Otherwise, you will get the real bounds on your system variables. Here's an application. This is Ben. He was a postdoc from my former lab. we worked on this problem based on the tools we developed. So fruit fly, it is trying to estimate the wind direction, the ambient wind direction, this value zeta here. If you are able to obtain this, the vector A and G, then you can calculate W. It is just vector mat. But fruit fly's brain primarily encodes the angle, so it doesn't have the these magnitude values. That's a problem. So you can't use the vector math anymore. By the way, I say primarily encodes angles because in biological systems, you can't say it doesn't encode. Maybe it does, but we don't know. So that's why we say it primarily encodes the angles here. So here we have the, we also add the heading angle here. So the fruit fly brain, it takes the heading angle information, the velocity angle, also the apparent wind angle, and somehow it calculates the ambient wind direction. And we are interested in the trajectories they are following. And we assume that they are maximizing the observability of the ambient wind direction by following certain trajectories. So we try to discover some observable motives. So we have a trajectory here. Let's see. There's some deceleration here. It's slowing down. There is a sharp turn. There is acceleration. There is an offset turn here, like dragging. It's not super realistic, this part. And there are some smooth turns. What we do is for each section, we build the observability, stochastic observability for a limited window size. And we are assuming these three angles are like observable. We build the observability matrix and take the inverse of it. And the sixth diagonal element will correspond to the ambient wind direction. So these are the results. These are not white. Actually, it's so unobservable, so you can't see these parts. But the wind direction becomes observable when there are some sharp turns or smooth turns. Otherwise, the wind direction is not observable. So these are corresponding to these minimum error variances. They are lower, that is, it's more observable. And then we try different sensor configurations. Let's say that in addition to the traditional three angles, let's say you are able to sense the optic flow. How does it change the observability of the wind direction? That's the question we ask. And in the last case, we assume that A and G are available. So it is like now it can do the vector match. So these are the results we get. So we already discussed this part. In the second case, sorry, turning, it was already observable, the wind direction. So adding a new sensor didn't make it unobservable, obviously. But also you can accelerate or slow down, and it can contribute to the observability of the system. So here there's deceleration and there's acceleration. And now you can observe the wind direction in those parts if you have the optic flow information. And in the last case, you can do whatever, your system will be observable. The wind direction will be observable because it can do the vector map some way. Do I have any more results? We have a code for these calculations. It doesn't include the process noise in this case, but we want this software package to be not just related to these results, but we want it to cover nonlinear systems, etc. So we just started this PyBounce package. So although I have so far discussed linear systems, hopefully this package will provide some tools for nonlinear systems with uncertainty. And it can even be partially observable because you can take that limit to obtain the observation limits on observable state variables, while some of state variables are unobservable. And one last thing, so this was all biology, but like observability problems are everywhere. Individual observability problems are also everywhere. So let's think about a battery. It can be your phone's battery. There are some variables you are interested in here. It can be state of charge of your battery, or it can be the state of health of your battery. So, you buy a phone, it works perfectly. After 3 years, the battery it's not as healthy as before. So that's the state of health of your battery. It declines the health. So it's like a dynamic system. You charge the system, the charge level goes up, and then it goes down, etc. So you have dynamic equations there. And you can take some measurements from your system, like the voltage measurement and the current measurement. Also, you can place some sensors on your system, like to sense the temperature. So half of the observability literature is coming from battery management, because they are trying to determine the state of charge and state of health of a battery, but they don't know where to put those sensors, the temperature meters, on their system. So they need a tool to determine the observability of that individual state variable. I didn't work on this problem yet, but that's a potential problem. And by the way, this is quite an important problem, because it's not about our phones, actually, right? It's sometimes about satellites. They also have batteries, and their health level also declines. And if you can estimate the health level, maybe you will plan a 3-month mission or 6-month mission. So it is important to determine the state of charge and state of health of your battery. There are more critical systems. And what I heard at a battery conference in Prague, so like some European companies, they dump their batteries, although they are still healthy, because they don't want their systems fail because of some battery issue, because they have to pay some penalties to the European regulators. If they are able to show their batteries are still healthy, they can actually use those batteries instead of replacing them. So that's an important problem. In aerospace, we have other problems. Let's say you are sending a rocket to the space, especially when in the takeoff, determining the bending mode is an important problem in that case. And where do you place your sensors to determine the bending mode of your rocket? So, or another example, I just want to give you the impression that these tools can be used everywhere almost. I was talking to some environmental scientists from Ljubljana, Slovenia, and they said they are placing some sensors in a city to detect the air pollution, but they don't have a methodology for that. It is based on their experience and their intuition. But now we have some mathematical tools to determine better locations, maybe, or optimal locations. Here's a sneak peek to my recent work. Do you have questions regarding the stochastic observability? I'm almost done, so let me take the questions later. So far, I discussed observability, which is the distinguishability of the first initial state of your system based on the present measurement and future measurements, which is not super realistic. There is another term called constructibility. You are trying to determine the current state, the final state, based on previous measurements and the present measurement. There's this, so let me try to go over this figure. So you have the system model, you obtain the observability graph mean, and it is interested in the initial state, and the constructibility graph mean is interested in the final state of your system. And if your system is noisy, then you build the stochastic observability graph mean and stochastic constructibility graph mean. And I recently show the duality of these gram means. So I came up with a dual system where the dual system's observability is equal to original system's constructibility and vice versa. And I told you that like inverting one matrix was super hard. Now, but there is a formula, a recursive formula in constructibility literature to obtain the stochastic constructibility gram mean. So now I can use that formula to obtain the stochastic observability gram mean. So we don't have to invert this matrix here, this huge matrix. Instead, we use that recursive formula. And this is the link to the to that study where we show the duality of these concepts. And that's all from me. Thank you for listening.